Hello friends, how are you? Hope you are doing well in your studies in universities and your profession, typically industry practitioners, and hope and the concepts we are discussing as a part of Six Sigma course must be helping you. So now as a part of lecture 50, I want to talk about operating characteristic curve for variable control charts. So we have seen in detail the design of variable control chart in the previous lecture. Now I want to discuss the operating characteristic curve for variable control chart as a part of lecture 50. Once again I would refer the statement and faith of a great quality guru, Imai, that control charts are one of the statistical tool for solving the quality related problem. He shows faith that yes, control chart can definitely help you to solve the problem and do the fact based analysis investigation. So we had a detailed discussion on need for control for both mean and variability. I may have both at nominal, say mean as well as variability, but I may have larger mean, larger variability or both. So in that case my products or services will fall in the rejection region, and basically I would be producing defective which is not acceptable to the market and customer. So if I have scrap, the entire value is lost. If I have rework, then again I have to do some processing, so that will further add the value and then say I can sell it to the market. So I will have extra additional cost to be incurred. So both the situations I don't want to enter. So it is better that let me have my process within the control, and we had seen the procedure for constructing X bar and R chart and the detailed example on X bar, S and R chart. So now this lecture basically will talk about OC curve for the X bar and R chart. So now just if I just hide this particular slide, then tell me what is the OC curve. We have already discussed when we started with the preliminary concepts and basics on control charts. I have already talked about OC curve. Can you recall? What is operating characteristic curve known as OC curve? So fine, I hope you have some ideas in your mind. So let us try to brush it up. So OC curve, an operating characteristic curve, is a measure of goodness of a control chart ability to detect changes in the process parameter. You have a gun, but it cannot fire. You have a sword, it cannot be operated. It is blunt. You have a knife, it cannot cut. So now we need to have a tool which has the power, typically called discriminatory power, really to separate out good and bad. So operating characteristic curve is a measure of goodness, how good my control chart is about the detection of change in the process parameter. There is a change in the process parameter, maybe mean or maybe variance, variability, and my chart is not able to detect it. Then what is the use of this chart? Unnecessarily I will be spending money on the maintenance of such chart, and it is just like a white elephant. So something can really be beneficial, it can have a utility if it serves the intended purpose for which it is developed. So here my control chart is developed to tell me that something is going wrong or something is going right, and if it cannot tell me, then there is a question, suspicion on the goodness of the tool, goodness of the control chart, and I have no use of maintaining such kind of system. So typically OC curve is the discriminatory power captures the discriminatory power of my control chart. So operating characteristic curve for X bar and R chart, we will see. We are talking about the operating characteristic curve for variables. Now just see that there is a type 2 error, and typically we call it as a beta. So the ability of the X bar and R chart to detect shifts in the process quality is described by their OC curve, and we will discuss on this part. So just think that there could be two things that can change. One is the shift in mean, other is shift in the variance. So your variability has got shifted from, let us say, sigma O to sigma 1, and your mean has shifted, let us say, from mu O to mu 1. Both the things are possible. Don't get confused by the notation. It's very simple. So my process may have shifted to a new mean. Maybe my bearings are worn out, maybe there is wear and tear, or maybe there are vibrations, or maybe there is an issue with the skill of the operator, and same is true with the variability. So now I have beta, that is type 2 error, and let us say mu 0 is shifted to, say, another value. Mu 0 is mu 1 plus k sigma. The probability of not detecting this shift is basically the beta risk. So what is type 2 error? Again, I will like to remind you that a jury is listening the case and there is a person who is guilty. So obviously he must be punished, but based on whatever evidences they have, they conclude that the person who is really guilty is innocent. So in this case, I am trying to make type 2 error, that is beta. If I convert now this into the process, I will say the process which is really out of control, or the process which is showing the assignable cause, it means it is guilty. So the process where the mean has got shifted or sigma has got shifted, I say that the process is in control, it is innocent. So this is where you will find that I am committing the type 2 error. We cannot 100% get rid of type 1 and type 2 error. Please remember, we always try to see the best trade-off. When we are dealing with the sample, we are not dealing with the 100% data. So obviously my say analysis is based on the probability, and I cannot get rid of type 1 and type 2 error. But yes, I want to see the impact of this on my ability to detect, and what can I do to improve the discriminatory power of my control chart. So I hope the idea is clear that why I am doing this. So let us say my beta is basically, my beta is probability that LCL is less than or equal to X bar is less than or equal to UCL for given mu is equal to mu 1 is equal to mu 0 plus k sigma. So now the mean has shifted to mu 1, and mu 1 is basically mu 0 for a given mu 0 plus k sigma. Mu 0 is your original position, center of your process. So now there is a shift. Now what is the probability that my X bar will fall within LCL and UCL? It means I am accepting that my reading is well within this specification, but actually there is something wrong. I say that it is the person is innocent, but it is guilty. I say that the process is in control, but actually process has gone out of control because there is a shift in the mean. So now with this understanding, I think the remaining thing would be extremely clear. Just see, I am repeating the generic understanding, because the moment you have to plot the OC curve, you need to know properly the type 2 error, your beta risk, and just see, this is the process under H0, null hypothesis, this is under H1. So when I say H0 means there is no shift in mean, my process is as it is, status quo is maintained. When I say H1, yes, there is a shift in mean, and now this has got shifted from this to this, and the difference or shift is delta square root of n divided by sigma. We have already seen this, it is just a revision. So now I want to find the probability beta, that is type 2 error, and for this particular diagram H0 H1, my process has got shifted from here to here. I want to find the probability that tells me that when there is a shift in the process, what is that region in this, or what is that probability which tells me that the process has not shifted or my process is well within the control. So typically you will see that this is the region which will give you the type 2 error, because it falls within the acceptance, but actually my process has got shifted. So after shifting, please remember, if I am not considering the case of shifting, it would be a different diagram. After shifting, what is that region or probability which tells me the beta risk, gives me the beta risk that I cannot detect shift or there is no shift and status quo is maintained. So this is my type 2 error, and this is the region which I am focusing on. So now easily you can compute, we have already done this, and just see that beta is equal to, this is the cumulative probability between z alpha by 2 minus delta square root of n divided by sigma. So it is the region between these two minus cumulative probability minus z alpha by 2 and minus delta square root n by sigma. So easily you can see that this is the region I am referring. So fine, this is my type 2 probability and it is called beta risk. If you have understood it, I think we are done. So now let us see, I am just trying to convert the basic equation generic understanding into more specific one, otherwise the concept remains same. So let us say x bar, which is the mean of my individual sample, it is normally distributed with mu and sigma variance sigma square divided by n. So my upper and lower control limits are, upper control limit is mu 0, that is as usual, plus L sigma divided by square root n. So this is the upper control limit. So I am taking L as the constant to find the upper control limit, sigma divided by square root n, and mu 0 minus L divided by, say, my sigma square root n. So when you do this, you get the upper and lower control limit, and I am just trying to put these values into previous equations. So these are the values. I can just go back to help you. I am just trying to put these values in the previous equation, beta cumulative value of this. So this will basically give me, if you carefully observe, put them one to one, UCL minus mu O plus k sigma divided by sigma square root n, LCL minus mu O plus k sigma divided by square root sigma divided by square root n. So I can now further replace the values of UCL by this particular one. So mu O plus L sigma square root n, LCL is this. I am just putting this value here, and this is already there, this is the new mean. So you have basically the expression x minus mu by sigma. So now with this, when I simplify this, this particular term is reduced to L minus k square root n. This is the cumulative probability, my phi, and this is minus L minus k square root n. So exactly this expression is nothing but, it is just an outcome of what we have referred here, it is this equation. So please do not get confused, this is very simple. And now let me try to see the development of OC curve and how I can interpret it for x bar and R chart. So I will just put the values. Let us say I am taking the value, suppose that we are using a chart with L is equal to 3, the usual 3 sigma limits. sample size is n is equal to 5. We wish to determine the probability of detecting mu1 is equal to mu 0 plus 2 sigma. So what does it mean? It means that my mu from the original position, it has shifted to 2 sigma, and mu1 is mu 0, which is the original one, plus 2 sigma. So I want to detect the probability, I want to check that what is the potential discriminatory power of my control chart in detecting such kind of shift. So I have L is equal to 3, K is equal to 2, N is equal to 5, and just see this, that in this expression what you need? You need L, you need K, you need N, and I have all the 3 values available. So I will just substitute these values here. So I have 5, 3 minus 2 square root 5 minus 5 minus 3 this, and this is minus 1.7 minus 7.37, and you can get the crisp values of this from the table, Z table, and you will get the probability value. These are the crisp values. You will get the cumulative probability for this from the Z table, and your beta is basically type 2 error, that is the probability 0.0708. Now what is this probability? It is the beta risk, and typically it is the probability of not detecting such a shift. Person is guilty, I am saying innocent. Process is out of control, I am saying it is in control. So it is my beta risk, inability to detect change in process mean shift or change in my variability. So I will say 1 minus beta is just the complementary event, that the probability that such a shift will be detected on the first subsequent sample. So 1 minus beta is my 0.9292. Now once you have done this, the remaining task is very simple. So you have to construct the control chart, OC chart, OC curve for the X bar. So you need to plot the beta risk against the magnitude of the shift we wish to detect in standard deviation units for various sample size n. In standard deviation unit means my mean got shifted by 2 sigma, 3 sigma, 4 sigma what. So the probability that shift will be detected on the rth subsequent sample can be easily expressed as beta r minus 1, 1 minus beta. I am considering both the event as well as complementary event, and my average run length will be, we have already seen this in detail, sigma r is equal to 1 to infinity, r beta raised to r minus 1, 1 minus beta, and the simplified version of this is 1 upon 1 minus beta. So let us try to see the graphs that will help us. Now this is the operating characteristic curve for X bar chart with 3 sigma limit, and beta is equal to probability of not detecting a shift on the first sample following the shift, means shift has occurred. After shift has occurred, I took the sample and I am not able to detect this on the first sample after shift has occurred. This is typically my beta probability of non-detection type 2 error. So you have beta, and these values you can compute as we have seen the sample calculation. This is K. So what does it mean? There is K sigma shift. When I say 0.5, it means you have 0.5 sigma shift in mean, 1.0 means 1 sigma shift in mean, 1.5 means 1.5 sigma shift in mean, 4.5 means 4.5 sigma shift in mean. Now you have the sample. So you can easily plot this curve which is called operating characteristic curve by finding the value of various values of beta type 2 error for your shift in say mean by K sigma, and beta expressions basically, if you recall, it needs your value of n, it needs your sigma, it needs the basically K, the shift, sigma shift, I can just show you, and it needs the n, it needs the K, it needs the L. So you have these values, and for different values you can plot a particular OC curve. Now each OC curve is for particular sample size. Now what do you see here? I have the OC curve for n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, 5, 10, 15 and 20. Just let me draw a line, and let us say there is a shift of 2.5, then I am just drawing a line. Suppose I am referring n is equal to 1 OC curve. This is the type 2 error, this is the type 2 error for n is equal to 2, this is the type 2 error for n is equal to 3, this is the type. So now what you can see, that as I am increasing the sample size, my curve is becoming steeper and steeper, and this says that the discriminatory power of my OC curve has increased with increase in the sample size, and hence I would be committing less type 2 error. So this is a very important observation, please remember. Similar way, I can plot the OC curve for R, and here I am considering lambda is equal to sigma 1 divided by sigma 0, because for R chart I am considering that there is a shift in the variability. My original variability, let us say sigma 0, it has got shifted to sigma 1. So now only this value will change, remaining calculation will follow the same expression, and you can compute the value of beta for the given n 2, 3, 4, 5, 6, 7, 8, 9, 10. Again you will see as the n increases, the discriminatory power means stiffness of my OC curve increases, and hence the probability of type 2 error, that is beta, it decreases. So I think it's a very interesting discussion. Now the another performance measure, there are two performance measures we discussed. Number one is the operating characteristic curve, and number two is the average run length. On an average, how many sample I need to take before I really detect the change in the process, and this is typically called my average run length. So I have two performance measures, one is OC curve, other is the ARL. So here your ARL is basically 1 divided by, we have seen this in detail, so ARL is 1 by probability 1 point plots out of control. So this can be given by 1 by alpha, and this is in control ARL. So this is for in control ARL, and when I say ARL 1, for the out of control 1 upon 1 minus beta. So we have already seen these expressions in detail. Now just let us try to appreciate this in terms of the OC curve. So or typically ARL curve here. So average run length curve for X bar chart with 3 sigma limit by K sigma shift. This remains same, the logic remains same. Here instead of beta I am putting the average run length. So now what you see here, these are the values of n. So as my n increases, again I am getting the better discriminatory power. My average run length for 2, let us say here for this OC curve n is equal to 1, average run length is, let us say, about 6.5. But if I refer to, it is 2.5. If I refer this, maybe it is 1.5. So what does it mean? It tells that if I am increasing the sample size, then on an average number of sample required to detect a change in process reduces. It means I would be able to detect the change early. So here again, say with the increasing n, my discriminatory power in terms of ARL is increasing. So obviously when you increase the n, the cost also is the important consideration. So I will not say that if you go for more and more sample size, higher and higher sample size, it is better. You need to be judicious in the sample size and the discriminatory power you need for a given quality characteristic. So fine, this is something that is really interesting, and same way you can put it for R. but here for a k I am just trying to see the expected individual limits to be detected shift, and this you can do very easily. So, interpretation of X bar and R chart, I have couple of interpretations in terms of some of the non-random pattern prevailing. So, there could be a cyclic pattern. Your chart is showing all the points within the control limit, but there could be some cyclic pattern present. So, this may be due to temperature, regular rotation of operator or machines, maintenance schedule, tool wear. There could be something called mixture pattern. So, when the plotted points tend to fall near or slightly outside the control limit, little bit. So, near or outside the control limit, two overlapping distributions are resulted from too often process adjustment. So, if you are adjusting your process too often, then it means that the resulting output may follow different distribution, two different distribution, and sometimes you may get a point very close to control limit, you may get a point slightly outside the control limit. So, this is the mixture pattern. Shift in process level, this may be because of say introduction of new worker, method, material, inspection standard. So, there could be shift in the process level. You may find trend pattern, and this is mainly because of some wear and tear or gradual tool wear, which is a very obvious phenomena in machining, and there could be a stratification pattern. So, points to cluster around the center line. So, you have a center line, and you will find that points they are forming a cluster around the center line due to incorrect calculation of the control limits or inappropriate say or reasonable sampling group. So, these are couple of reasons. So, let us try to see each one through a picture so that the idea becomes extremely clear. It is a cyclic pattern, you can see the cycle is formed. The reasons I told. You can see another, that is the mixture pattern, and you see the points are falling very close to the control lines, maybe upper or lower, and this is typically called mixture pattern. So, two populations are mixed, two distributions are mixed, and sudden shift in the level, you can see there is a gradual increase and sudden shift in the level. You can see gradual shift in the level. So, shift is taking place, but it is gradually, and this is your gradual shift in level. There is a trending pattern. So, some trend you can observe, maybe because of wear and tear of the tool, bearing, or some other say equipment, say component, or there may be some error in the measuring instrument. There is a stratification pattern, and what do you see here? That points are more or less concentrated around the center line, and this kind of stratification pattern may be because of wrongly calculated upper control or lower control limits, or maybe some problem in the sample size or reasonability you have criteria you have considered for number of sample and sample size. So, this is what you can appreciate. There could be a wild pattern, and what you see that up to some extent it is well within, and then suddenly it jumps and there is a wild pattern. Again suddenly it jumps and there is a wild pattern. So, these are some of the typical causes. Maybe let us say because of some reason there is an excessive vibration in the machine, and you may find that there is a sudden jump or there is a wild patterns. So, typically we go through different patterns, and we need to appropriately interpret it. One more pattern that you can see is the interaction pattern. So, here what do you see, that you have two variables, and if let us say one variable affects the behavior of the another variable, then there is some say interconnected or interaction pattern present. We have seen in ANOVA that there could be an interaction effect, and we have checked it statistically. So, let us say these are the sample averages as usual. This is my upper and lower control limit, this is my upper and lower control limit. Now, this is temperature level A and this is temperature level B, and suppose if change in level can have some interaction or impact, you would find that after some time, say when you have changed from level A to level B, after let us say 10 sample, you have different pattern to observe. So this could be because of interaction. Now before we end, let me float couple of thinking questions that can help you to introspect and revise. What is OC curve? What is its utility for control charts for variables? What are the key features of OC curve? How do you interpret the various patterns in the control chart? And what are the critical dimensions of the control chart? There is a small situation. A financial institution wants to improve proposal preparation time for its client. Discuss the actions to be taken in reducing the average preparation time and the variability of the preparation times. So I think with this you have acquired the adequate knowledge on operating characteristic curve for control charts for variables, and these are the references you can use to have better understanding on this particular topic. So OC curve is a discriminatory power and is a measure of goodness of my control chart, and typically it relates the specific shift in mean or variability with the type 2 error. As I increase the sample size, the discriminatory power increases, but also I have to see the economics, and the one which can give me the best trade-off, I must go for that particular operating characteristic curve. So thank you very much for your interest in learning operating characteristic curve for variables, control charts, and keep revising. Take some data, hypothetical or real. I emphasize again and again and try to internalize the concept. Thank you very much. Be with me. Enjoy.